Welcome to solverfy.
In this problem, we have three materials with indices of refraction N1, N2, and N3. We're given that the indices of refraction are N1 equals 1.6, that's a 1, N2 equals 1.4, and N3 equals 1.8. We're also told that the thickness of the middle layer, L, is 200 nanometers. And we're asked what wavelength of visible light can we shine in here such that no light reflects. So for no light to reflect, it means that these two rays here, R1 and R2, which are rays that are reflecting off the first surface and the back surface, so R1 reflects off this front surface and R2 reflects off this back surface, that they have to come off half a wavelength out of phase, such that one ray looks like this and the other ray looks like this. And so the net amplitude, when you add these together, is 0. So that means that the path length difference, which is twice L, because you go once to the right and once to the left, so 2L must equal a half multiple of the wavelength. So this is the wavelength, lambda. We can write it this way, where m is an integer starting at 1. So everything is going to be, so we have 1, and then minus a half is a half, and then we can put in 2 minus a half is 3 halves, etc. Now we have to be careful because the wavelength in the material is not the same as the wavelength in the vacuum. So we have to write this as lambda sub n to indicate it's lambda in the material with index of refraction, and in this case it's going to be index of refraction n2. And lambda sub n in general is the vacuum wavelength over the index of refraction. There's one more thing we have to account for here, which is that when a ray reflects off of a material, if it's going from a lower index of refraction to higher index of refraction, the reflected ray gets shifted by half a wavelength. So we have to check for that. N1 to N2, we're going from higher to lower index of refraction, so there's no phase shift. But N2 to N3, there is a phase shift when you reflect. So that means that this whole thing is actually now off by half a wavelength. So we got to add another half a wavelength to get back to where we want it to be. So we got to add a 1/2 here, which ends up canceling out this 1/2. So we can cancel this 1/2. So in total, we have that 2L must equal lambda n, which is lambda over n2, times some integer m. Plugging in the numbers, we can solve for lambda. Lambda is going to be 2L times n2 over some integer m. And if we plug in the numbers, we get that this is 560 nanometers over some integer m. And we just have to make sure this is in the visible spectrum. Now, the visible spectrum is about 400 to 700 nanometers. So this is in the visible spectrum. So we can just set m to 1 and we'll be in the correct range. Oops. Right, so we can just set m here to 1 to get that lambda equals 560 nanometers.